So, hello everyone. Welcome to the June edition of our Brainfood Talks. In our channel, we are showing once per month IT-related topics. So, if you're interested in those kind of content, you can stay up to date and in tune by following us at meetup.com. Also on LinkedIn, you will find the most recent information of what kind of topics we are presenting and when we are presenting. So I'm very much encouraging you to follow us on Meetup or on LinkedIn to stay up to date. Very good. So I will be talking today about platform engineering. My name is Jerzy Kirchner. I'm the head of cloud and platform engineering here. And what we want to discuss today is what platform engineering is, how we even arrived at the problem, and what kind of solution we can have in order to improve the world a little bit. Very good. So first, let's talk about how we even maneuvered into a problem and why platform engineering even became a thing. So I'm not sure if you are following YouTube and you are following some other media, you will also recognize that right now at this moment of time, there is the PlatformCon currently going on. So if you're interested in platform engineering, I think there is also quite a lot interesting content. Good. So let me start the story at the age of waterfalls and big bangs. Where else could we start our presentation? And when we think back of how we have organized ourselves probably 10 years ago, for some companies, it might be maybe not 10 years ago, but a little bit less. But what has happened is companies had usually kind of an application development department. Those application development departments have done changes and maintenance on their software systems. And whenever something big should be changed in the systems, we usually established projects. And to do projects, we had like, I would say, project-centric teams. There might have been business analysts inside, there might have been testers inside, there might have been project managers inside, and so on. And those two, the application development department and the central project teams, have like came together. They have been working on the changes for sometimes 6 months, sometimes 12 months. And then once they have been ready, everyone was happy, and things have been packaged and been thrown over the wall to the operations people. And I think every one of us knows how this ended. So there's a couple of problems with it. The first problem is that waiting for a change for 6, maybe 12 months or even longer in certain cases is quite bad, because what we have developed might not be relevant anymore at this time. Maybe we have even implemented the wrong thing and we had no possibility to react on it. And also throwing things over the wall created a lot of stress on the operations people, and they've been really, really poor people. So what has happened in a next iteration is, so we understood we need to change. So the Agile and DevOps movement have been initiated. So in the Agile movement, we realized that not waiting for 6 to 12 months is good. So we want to deliver in smaller chunks. And how can you deliver small chunks very quickly? By getting rid of all your dependencies. So what has happened is we've restructured the teams into maybe product streams or some product silos. And all people who are involved in creating the software have been like pulled into those product streams in order to cut off dependencies and make things faster. And with the DevOps movement, something very similar has happened. So to get out of the situation that we are creating something and throwing over the wall after a couple of weeks or months to the operation teams, we also pulled in the operations people into each of the product stream. And this is what we, in fact, have called DevOps, right? So those product teams have gained like full autonomy. They have been responsible end to end for the delivery of their products. And they've been working in a mode which is, many people call it, you build it, you run it. So meaning that we have like a full feedback cycle of what we have released to production and can very quickly react on it and take it to the next iteration. So after delivering our software quite fast, we have discovered that there is another bottleneck, and this is our infrastructure. So it came kind of naturally that we have jumped on the cloud movement. So meaning that there have been the hyperscalers or public cloud providers like AWS, GCP, Azure, who allow you to very quickly and very easily provision your infrastructure. And the situation was following that those product streams on their own had to figure out how to use the cloud most efficiently. In many cases, companies have introduced like one layer of compliance. So this was rather to prevent people of doing things which are against the rules, against the security, to avoid that we are doing the wrong things, but this compliance layer did not necessarily give us any, I would say, guidance on how to use the cloud. So, and what I would like to discuss is how the situation feels from the perspective of an engineer and what an engineer has to do in such a product stream in this situation. So the first and most important thing is, so engineers in product streams should be solving domain business logic, write new source code, trying to create something which makes our customers happy. So this is where certain time of our day is being consumed by. The second thing is, so we are now in the cloud, so it's the perfect time to deal with, so chop down our business logic into microservices, meaning we learn how to deal with domain-driven design. We understand how to work with microservices. In order to realize microservices properly, we learned how to use containers. We learned how to package software properly. We learned about the 12-factor apps. By chopping down an application into smaller chunks, you run into all problems which are related to designing distributed architectures. Be it that the network is not reliable, you could lose packets on the way, maybe an interface which you need to call in order to fulfill your business logic might not be available in a certain moment of time. And there is a lot of cope with in order to design for distributed architecture. And in fact, maybe friends of us told us that there is a perfect solution for this situation, and it's called Kubernetes, and it's called service meshes. But in fact, we are realizing that those kind of technologies are adding quite a lot of complexity to our architecture. Next is we have gone to the cloud. If I'm looking at a toolbox of big cloud providers like AWS, so we are exceeding currently the 200 number of tools which can be used to solve my business problems. So there is actually quite a lot of complexity also coming from the cloud providers. We need to take care of observability. We need to take care of the operations of our new application. We need to take care of the increasing complexity of our CI/CD pipelines. In fact, we also need to keep the whole system secure, right? So we need to incorporate zero trust and all the security requirements from our departments. And in fact, what happens is we come into the situation where our engineers are suddenly feeling overloaded, and it makes like a big kaboom. So, and when we've reached this point, we suffer as engineers a problem where suddenly, so we gone into those product silos in order to be faster and to deliver features more iteratively, but suddenly the surroundings of where we are incorporating the software in is getting more and more complex, and having this complexity on the table instead of making us faster is making us much slower. And I would like to understand how it came that this big kaboom was created happened. And for this one, I would like to zoom in into the brain of an engineer. And we can also use a quite handy tool, which is called the cognitive load theory, which was created by John Sweller in the year 1988. In fact, John Sweller has understood a couple of things. So he comes from learning theory. So meaning that he was trying to understand how people are studying and what makes them most effective. And he understood a couple of important things like short-term memory is super important for learning. He also understood that in order to understand something, we are building internally like models of the topics which we try to learn. And he also understood that brains have something which is called cognitive capacity. So you can imagine the cognitive capacity to be like the maximum load a human brain can take in order to process things and in order to cope with the complexity which we're involved in. And he tried to understand what kind of factors are contributing to the cognitive load, or which are consuming the cognitive capacity of our brains. And he has identified three pieces. The first one is the intrinsic cognitive load. We have the germane cognitive load and the extraneous cognitive load. And if we switch from learning theory to our engineers' lives, then intrinsic cognitive load means, so it's the load which is created by executing my daily task. Let's say I am a Java programmer and I'm quite a pro in it. Then the brain capacity which I need to use in order to solve a complex problem in Java is much less because I'm familiar with the topic than for maybe a bloody junior who does not know how to do object-oriented design properly, who does not know how to deal with concurrency and many other things which create a lot of issues and also increasing the intrinsic cognitive load. We also have the germane cognitive load. So this is what we would say is the important one. So this is where we try and solve the real problem which we are working on. So here we are solving our business domain. Let's assume we are building a complex markets application which needs to process things in real time. So the germane cognitive load is the one which arises when we try to understand, okay, what kind of APIs do I need to fetch my data from? How do I cut the architecture for it? How generally I'm coping with the business domain which is at hand. And then we have the third one, the extraneous cognitive load. And this is everything which I would say is on the outside of your ecosystem and which you maybe cannot necessarily influence. So again, to see it from the glasses of an engineer, it might be that you want to deploy your backend service and you need to do it on Kubernetes, but actually it's quite difficult to do. You have very little knowledge about Kubernetes, but you need to use it. Or let's say you need to have an OAuth client ID in order to go live to production, but in order to request it in your company, it's getting really, really difficult. You need to file somewhere a ticket, but you don't know where. You have created it, you need to wait for a couple of weeks. So it's actually taking up capacity of your brain, which you could use in a different way. And in fact, what I want to talk about is, so we understood that germane cognitive load is the important one. So we want to increase it as much as possible. We want to use most of the capacity of our brain for the business tasks. The intrinsic cognitive load, there is only one way to reduce it by doing, let's say, training, maybe on Java, maybe on some other topics, which I'm working on with on a daily basis. But the extraneous cognitive load, so the working environment in which I am creating my software on a daily basis, is something which we can simplify and we can make easier for our engineers. So meaning that, in fact, the rest of the talk, we will be talking about how we can improve the working environment of our engineers, to reduce the extraneous cognitive load, to improve the germane cognitive load, and in fact, leaving more space to work on business domain problems, and in order to avoid cognitive overload. We will present 3 strategies for it. In fact, it will be 3.5, but let's walk through it piece by piece. So the first strategy, in order to cope with cognitive extraneous load, is to build platforms. And the word platform and platform engineering became quite popular after the book Team Topologies have been released. It was around 2019. It was written by Matthew Skelton and Manuel Pace, which are coming from a perspective of they tried to understand how to incorporate DevOps properly on an organizational perspective in companies. And from understanding like good patterns and anti-patterns from this, they realized that they can take it even one step further and formulated, let's say, an organizational pattern, how teams in organizations should be cut. And they have come up with something which they call the team topologies. And they are stating that each and every company which is creating software should be split up into 4 types of teams, which you can see on the left side. So the first type of team is the so-called stream-aligned team. So stream-aligned teams are the ones who are working on a daily basis on your business domain, who are creating software for your customers. In fact, they are the ones which are bringing in the money to your company. And then we have the enabling teams, complicated subsystem teams, and the platform teams. And those have one very important task, and this is to do everything which is necessary in order to improve the lives of a stream-aligned team. So let's take, for example, an enabling team as an example. So stream-aligned teams are working on a daily basis to solve customer problems. So maybe they are spending their times in building different versions of the same feature to do maybe some A/B testing. They try to understand their customer in very much detail. And maybe they are missing time to stay up to date with the latest and greatest trends in technology. Let's say they have fallen behind with test automation. So this is where enabling teams come in. So enabling teams are spending 100% of their time maybe on test engineering, test automation, and try to stay at the cutting edge of what is currently possible and trying to figure out how they can teach other teams in order to bring this information and spread it. So when stream-aligned teams, so the yellow ones, are falling behind, then the enabling teams, the purple ones, are joining them, maybe for a period of 4 weeks, 6 weeks, maybe 8 weeks, trying to bring them up to speed. And once we have catched up with test automation, the enabling team is being removed in their interaction with the stream-aligned teams, and the stream-aligned team will be on their own, and the enabling team is helping someone else. And in a very similar manner, we have also the platform teams. And platform teams do not help with knowledge, but they are helping with tools. So the task of a platform team is to create an environment, create the tooling, create everything which a stream-aligned team needs in order to build their services, and make this creation of the services as easy as possible. And if we jump back to our picture, which we have previously seen with our cloud and with our product streams, so the product streams would be the ones which Team Topologies is calling the stream-aligned teams. So those are now the yellow ones. And the platform team, and the platform is sitting right in the middle between our infrastructure. So it might be cloud resources. It might be maybe your internal infrastructure, which you're using. And what's the platform and platform team is doing? It's creating tools in a self-service manner. So what does self-service mean? So we try to achieve similar experience like if I want to create an EC2 instance on AWS, I can do it completely on my own, right? I go to a web interface, I might consume some APIs, and I never, ever need to talk to someone from AWS in order to create those resources. And the same way also a platform team should operate, right? And the second task is the platform team with a platform has a second goal, which is reducing the cognitive load on the product streams. And how do we do it? We do it by abstracting away the complexities of a cloud provider, of your internal infrastructure, and all the other tools which are existing in the ecosystem, which are raising cognitive load. We will speak about how to do it in a minute. But let's first look at what platform is content-wise. And this one is kind of difficult to explain because every platform is different and every platform is solving a distinct problem. But in fact, what many platforms incorporate is multiple layers of things which kind of repeat. So the first one is many platforms are managing like the base infrastructure. So let's say I want to have, I want to deploy a container. So it might be that the platform engineering team with the platform is providing me computing resources to run my containers, like maybe ECS. I might want to expose my service on a gateway. So the platform team provides me the possibilities to configure the gateway on the networking layer. Maybe I want to have, a new Kafka cluster. So this is where storage will be provisioned for me. The next layer on top is like cross-concerning tools. So we are working in a microservices environment. So maybe it's quite difficult to figure out what is going on with my individual microservices. So they might provide me some instances of Prometheus or maybe Datadog or some other tooling. Many platforms also take care of the security and compliance parts. So identity providers, there might be some compliance tools which make sure that that we are not deploying anything on our platform which is forbidden by the rules of our company. Then a very important thing is we said that we want to reduce the cognitive load of our engineers by abstracting away the underlying infrastructure. And this is what this abstraction layer is about. We will talk about this one in more detail, so I skip it for the second. An important topic also in many platforms is pipelines. So meaning how are we delivering new artifacts to our target environment? How do we make sure that they are staged properly? And providing maybe artifact repositories, providing some repeatable building blocks for our CI pipelines. And then we have also something which we call the platform interface. So the platform interface provides us, I would say, a view on the underlying platform. We will also speak about this one in a second. Another component of platforms, which is super interesting and very, very important, in fact, it's one of the probably most core ideas of a platform, is not the technical aspect, but rather an organizational one. So what is available in all the platforms is like platform management. And platform management means that when we are building a platform, we want to start treating our engineers as if they are customers. So what does it mean? That we need to find out what are their daily problems when they are deploying new pieces of software to a production environment. Where are they roadblockers, right? How can we make their lives easier? And for this one, we are running through a very similar let's say procedure as we would with real customers. So we start to do some user research to find out what's going on. From this one, we are building our backlogs. We are defining roadmaps to make people understand what are we going to deliver next and second next. And then we're implementing like like an MVP. In platform engineering, it's not called MVP, but it's called the TVP, so the finished viable platform. So we are creating some improvement in engineers' life. We are deploying it, bringing it back to engineers, trying to understand, is it really what you need? Is it really what solves your problem? And if yes, we like repeat the process again, going to understand with user research what is the next pressing problem and improving lives piece by piece. Good. So we understood what generally a platform is. So platforms provide self-service capabilities and do abstractions in order to make lives easier of our engineers. And now let's talk about the abstractions itself. So what does it mean? So if I want to deploy, let's say, a backend service, and I'm now staying on the side of Kubernetes because I think many of us are using it. In fact, what you're doing in order to deploy a backend service, you create a deployment YAML manifest. And in this deployment YAML manifest, we are specifying like what image should be deployed in which version. We also provide environment variables. We are providing like the number of replicas, but there's also quite a significant amount of, I would say, boilerplate code, which is not necessarily helping us in creating the deployment. Maybe we want to connect to external resources like a database, maybe an API. And in fact, if you're not familiar with Kubernetes, then Kubernetes is not encrypting their secrets by default. So in many times you're like installing tools like in this case sealed secrets operator, which help you to encrypt your usernames, passwords, credentials, whatever. So this is also what I need to take care of. I need to create a secrets YAML and provide the secrets which I need to connect to my database or external service. I want to expose my service on a gateway, so I need to configure my ingress. I might need a little bit of disk space to store some information in which is being generated during the process. I might define my alerts. I might need to have a couple of certificates. I might need to create some external resources like an S3 bucket or something. And what kind of feels wrong in the very first moment is that even though we just want to deploy a backend service and expose it to the public world and maybe secure it, we are creating a lot of YAML files. And I want to explore in a little bit more detail, how do we even come to the situation that so many YAML files needs to be created? And in fact, if we are looking at the different layers of our infrastructure, what is happening is we are walking layer by layer by layer, and trying to understand as end users, okay, I'm building a backend service, so meaning I need a bit of networking, so meaning I want to create an ingress. And on the security layer, I'm specifying that I want to secure my API, so I need something from my identity provider. And I need something from observability, and I need something from other layers. So what is happening is by me as an engineer walking through layer by layer, I am trying to, so I am the one who is specifying what it actually means to be a backend service which is exposing a REST API, right? And this is kind of creating a lot of problems. And the first one is the granularity of this approach feels kind of wrong, right? So I'm walking through layer by layer, and I need to specify a lot of YAMLs. It kind of feels like I'm trying to create a game and doing it by drawing individual pixels, but it should be a 3D game in the end, right? So the granularity seems to be off a little bit. The next thing which is also bothering me is if I want to define on each individual infrastructure layer what I need in order to be a backend service which is exposing a REST API, I need to have quite a detailed understanding of what each layer contains, what kind of operators are running on it. So we've seen, for example, in order to provide the secret, I need to understand that there is this yield secrets operator installed in my infrastructure. And in fact, I even need to understand how it's working, how am I encrypting my secrets, maybe by using a CLI. I need to understand what it means if a secret is bound to a namespace. I need to understand what it means if they are bound to the cluster. So there's a lot of detailed information I need to understand about my infrastructure layers just in order to be able to provide the correct YAML specification. And the last problem which I see is not on the engineering side, but more on the platform engineer side. So when we are exposing each layer without any abstraction or any layer which is simplifying those things, we are like exposing the inner core of our platform to our engineers. So let's stay with the example of sealed secrets. So we are encrypting secrets, checking them into our GitHub repository. And after maybe 6 months, the security team has understood that we are checking in secrets to our source code repository, even they are encrypted. They might say, oh, you know what, we are kind of unhappy with this approach. Please remove the sealed secret operator and replace it by something else. And in fact, you as a platform team might be already in the situation that hundreds of repositories have been created already in this approach. So it's becoming very difficult to change this behavior because there's already so many dependencies on each individual teams. So you're cutting like your own autonomy or your own speed to go forward. So meaning this approach does not seem to be a good one. It's kind of not a perfect solution for engineers nor for the platform team. And the question is, can we do better? And this is where we speak of vertical slicing, right? So imagine we are not specifying our APIs layer by layer, but we are specifying them vertically. When I, as a platform team, know that what you want to deploy is a Java REST backend, then I can take a lot of assumptions about the infrastructure below and what kind of pieces you will need for sure. So I know very much that you try to deploy a container. I know that you will need an API gateway because you're trying to expose a REST endpoint. I might even know that he wants to, deploy it to the public world. I might know that you need an OAuth client ID because this is our standard in the company, how we are securing our APIs. So a lot of assumptions and a lot of defaults can flow into such a vertical platform API. And we can do the same also with other use cases like an Angular customer frontend or maybe an analytical workload. Yeah? And what in fact is happening is by taking all those defaults and understanding what we try to deploy, we can reduce the specification to a super minimum set of questions. So on the right side, and please don't judge me if this is a good API or not, but we've reduced the input parameters which engineers want to or needs to provide to an image environment variables. We maybe ask them what kind of database they need, and we might ask them, do you need to expose it to the public, yes or no? And depending on this input, we're like generating the detailed specifications and the detailed configuration for our engineers instead of asking them on this detailed level. The big question is also, how could we achieve this? So for example, in a world of Kubernetes, there is a lot of possibilities. Let me pick the operator framework. So the operator frameworks allows you to specify your own custom resources. So you can actually define what are the detailed parameters which we are asking. And you can also create business logic which takes those parameters and either explodes them to this more complicated world on the left side. You can do a very detailed checks on the value ranges of your input parameters. And by incorporating the operator framework and building your own operator, you could solve such kind of a problem very easily. But there is tons of other tools which you can use for and fulfilling like the same approach, right? So you could do it with crossplane, with specifying compositions, right? You could do it with Terraform by providing modules which are slicing vertically. So there is a lot of possibilities which you could use to achieve the very same. So, and now we come to strategy 2.5. So we've understood that we should build like vertical APIs. And the big question that arises is, so what should we even verticalize? And this is where golden paths come in, and they help us to specify what a platform should do and which are the important things we should watch out for. The golden paths is something which has been specified or defined by Spotify. They are coming from a bit different angle. So they have been in the situation that after their very fast growth, they've been consuming almost every technology which is out in the market, and they've been experiencing quite significant technology fragmentation, and they like thought about the golden paths, how they can improve the situation and how to reduce the complexity of their technical environment and also to streamline things a little bit. And what they have been thinking is if you want to reduce the number of technologies used in your company, you could go in both directions. So one is you could implement a very strict governance. So strict governance might mean there is a body of architects which are specifying in the worst case, whenever you write business logic, you must use Java, and there is exactly one framework which you can use. And whenever you are writing some scripts, you need to use Bash. And whenever you are not following those rules, then in fact, you are contradicting or you are breaking the rules of the company, and people will get very angry. And in fact, this is causing a situation where engineers get very I would say tired of this approach because they feel restricted by it. They do not feel happy. They cannot. They have too little freedom in order to implement whatever they need to do in their daily life. The other side might be full autonomy, right? So if every engineer can do whatever they want, they will choose probably the technologies which they are most familiar with the most, and which leads to the very opposite problem, right? So if everyone is choosing the technology they want, then maybe one team is creating a front end in Vue.js, the other one in React, the other one in Angular, the other one in something maybe else. And once you need to maybe roll out a new corporate design, you are running into a problem because you have so many technologies. And this is also what Spotify has experienced. And this is what we call the speed paradox. So we go over the line where we have this very much speed up in the beginning, and suddenly our environment is so much different in all its small pieces that instead of being faster, we are suddenly getting much slower. And on the other side, we have the speed paradox. When everything was the same, then changes on a big scale are becoming suddenly quite easy, right? So, and golden paths try to be somewhere in the middle. So Spotify defines that golden paths are not trying to be super strict in a governance manner. They also don't want to give you full autonomy, but they try to be in the middle. And how do they do this? They are specifying like the path of least resistance, how you can, for example, create a REST backend in Java. And if you want to create a REST backend in Java, if you are following the golden path, you exactly know that you will reach a goal very, very, very easily. But if for whatever reason it restricts you, you can always decide to leave the golden path. So you say, I want to do it differently. So you can implement your stuff in a different way. But what you must be aware is that there will be no one to help you. So you are kind of leaving the path, going into the dark forest and being on your own. And the second thing is there might be more than one golden path. So if there is, let's say we are in the front-end world, so building a customer front-end which is super polished, might be being built with a different golden path and with different technologies than we are building for our internal employees, where things maybe are not as shiny, but highly functional. So, and in fact, this idea of defining those golden paths is also helping us with our platform engineering, because what we can do is we can walk through every layer of, let's say, the journey, how we are building our services, and understand, for example, okay, how to structure our source code repository in the most appropriate way for this kind of golden path. What kind of, how does my ideal pipeline look like? How do we implement, let's say, a very well established set of tracing, monitoring, and alerting, right? So we can walk this golden path and understand what is the ideal way in our company to solve this problem. And the second thing which we can understand is where on this way we are in a situation where things are not working proper. I, for example, named before, in order to release a backend service written in Java to production, I need to have a client ID. But ordering a client ID is a super manual process, meaning that even I could deliver my software every second week, I'm still stuck waiting for an infrastructure team to throw over a ticket and wait for it like for 6 or 8 weeks in order to be my to create my small piece of configuration. And so if we walk through these golden paths, so to return back to these layers, in fact, the use cases which we've been speaking of can be and should be even those golden paths which we have been walking through. And by understanding the golden paths in detail, we can derive a lot of things for our platform also, right? So we can derive a priority. So we understood that client IDs are making a trouble. So the first thing we should solve in our platform to make it easier to be consumable by our engineers might be client IDs. From what kind of problem we try to solve, we also derive the building blocks. I said before that it's a bit difficult to define what a platform is because every platform is different. And here you can see that depending on what golden path I'm trying to solve and where are the problems on my golden path, my building blocks might be significantly different than in another platform. And the third thing I can derive from it is the vertical platform APIs, because by walking the path and seeing where do I need to have freedom and what are usual cases to take defaults, I can start reducing my vertical APIs to a bare minimum and see where people need freedom and where they don't. Good. So let's go to the third strategy. And this is developer portals. And developer portals kind of bring things together. So meaning that if we are again looking back at our exemplary picture of our developer platform, it was the top layer. And developer portals are usually taking 3 tasks. One is the components catalog, one is the centralized information, and the third one is templates. So the components catalog tries to answer the question, what is running on a platform? So I've been in many environments where we have the very same problem. Like we have gone towards building microservices. We've created a lot of APIs. And once you are creating your microservice and want to consume an API, which has been created by another team, usually it's very difficult to even find out what kind of APIs are existing in my company, right? And this is where developer platforms come in. They catalog components which have been created. So those might be services, this might be APIs, this might be databases, this might be external software as a service tools. And it tries to catalog them so everyone is aware of what is available in your environment. And cataloging those things usually does not happen automatically. So there is a couple of different contenders for developer portals. One of them is being sponsored by the Cloud Native Computing Foundation. It's called Backstage. And the backstage, for example, pulls this information from the source code repository. So you just need to let backstage know which source code repository to look at and provide a little bit of metadata, and it's being pulled from the source code repositories. So you usually are not maintaining this information manually. So there is another thing. Once we have understood what components we have in our platform that are running, we can start pulling in a lot of information about those components. Let's say I want to know, is this component currently deployed to the production environment in the most recent state? So this information might be somewhere hidden in my in Argo CD. So I can pull this information from Argo CD and display it right beside of my component in the developer portal. I could also ask other questions like how costly is it to run this one API? So I could query the Cost Explorer APIs of AWS and show the cost consumption of this one API together with my component. The same, I could display how often was my API invoked, right? So there is a lot of information I could pull in from the below layers in order to bring the information to the component and not making it hidden in the down layers. And the third thing which developer portals are helpful with is instantiating new components. So let's say we have created our golden path and we've understood what it means to create our best practice Java backend service according to our company rules, according to developer experience and whatsoever. So we can use templates to scaffold source code repositories, which pre-configure everything as we think it's the best way. So this is what templating can do for us. And ideally, in a perfect world, these templates, which have been instantiated through the source code repositories, are registered at the very same time with the developer platform, being picked up, being deployed automatically. So meaning after instantiating my template, you are in the situation that your maybe just the shell of backend service is being deployed to the target developer environment or dev environment, where the gateway is pre-configured, where my client ID is being pre-configured, where my secrets are maybe pre-configured, where a lot of other things are already there. And what stays as my task is to fill in the business logic to make the backend service do whatever it needs to do. So this is like the ideal scenario where we want to be. Which also means, in fact, that there must be a lot of automation around it to bring it to this level of maturity. But I think it's always good to have the end goal in mind. Good. So going back to our picture of the cognitive capacity which our brains have, we have tried to improve our German cognitive load and minimize our extraneous cognitive load. And in fact, we've applied 3 strategies. So the first one is building platforms to have self-service APIs and to abstract away things by improving the cognitive load. Abstracting away happens best with vertical APIs. So we are slicing by use case and not by individual infrastructure layer. And the third strategy is to introduce developer portals as they are bringing a lot of information together, not distributing the knowledge about what is running on my platform, what is the current state of my components, bringing things to one place, and also reducing the extraneous cognitive load. And having implemented those things, hopefully our engineers are again in better mood and not feeling overloaded anymore, and working in an environment which makes things simpler instead of harder. So this is the end of my presentation. And what I would like to do is to look just a second in to questions. So one of the questions which we have is, do you think Vanilla.js will take some or more work away from front-end frameworks due to the framework fatigue? To be honest, I don't know Vanilla.js, but I would Google it up later on. So, Niklos, if you are interested, then maybe you can contact me via LinkedIn, and let's have a conversation on it. It's quite an interesting topic. Let me see if other questions are coming in. It does not seem so. Very good. Then, so I hope that you enjoyed the content of today's Brainfood Talk. If you want to get in touch with me, you can do so by contacting me via LinkedIn or via email, and I would be happy to have a conversation with you. Otherwise, just for information, there will be no Brainfood Talk during summertime due to the summer break, but we will come back online in September, and we will announce what kind of talk will be the next, probably via Meetup, LinkedIn, and if you want to follow us, maybe you also want to subscribe to this YouTube channel. So thanks a lot, and hopefully hear you soon. Bye-bye.